In fifth lecture, we will mainly discuss the linearity property of Laplace transform, and we will also discuss some examples. Around 4 examples we will discuss, and different cases also. And in the last portion, we will discuss the solution of lecture 4 practice questions. And coming to the linearity property, the general equation for finding the Laplace transform is x of s equal to integral minus infinity to infinity x of t e raised to minus st dt. And let the Laplace transform of the signal x1 of t is equal to x1 of s, and the ROC is R1, and Laplace transform of another signal x2 of t is equal to x2 of s, and the ROC of that particular signal is represented as R2. So there are two signals, okay, and transform x1 of s and x2 of s. And if there is a signal in the form ax1 of t plus bx2 of t as a linear combination of two signals where a and b are constants, and then we can find the Laplace transform the combination of these two signals by using the equation, okay. But instead of using this particular equation, we can directly find the Laplace transform if you know the Laplace transform of x1 of t and x2 of t. It's simply the sum of the Laplace transform of these two signals, and corresponding constants are multiplied. So the result will be ax1 of s plus bx2 of s. And about the ROC of the new signal will be like this, at least R1 intersection R2. So common area we need to consider, okay. Minimum you will get the common area, okay. Sometimes you will get more than that. Now we'll see different problems related to linearity. So this is the first question. Find the Laplace transform and ROC for the signal x of t is equal to e raised to minus 2t into u of t plus e raised to minus 3t into u of t. So there are two signals. The two signals are causal signals. So I can take the standard form. So this is a standard equation which we discussed in lecture 2, e raised to minus 18 into u of t. If there is a signal in this form, the Laplace transform will be 1 by s plus a. That is a causal signal. The signal exists only in the positive side. Then the ROC will be either we can say real part of s is greater than minus a. So here it is minus a. So you can write real part of s greater than minus a, or simply you can write sigma greater than minus a, because s is defined as s is equal to sigma plus j omega. So based on that you can write real part of s is equal to sigma. Now based on this I can write the result here in the question. One part is e raised to minus 2t into u of t. So this is one signal, so its Laplace transform can be written as 1 by s plus 2, okay. This is 1 by s plus 2, and the ROC you can write sigma greater than minus 2. So we got one signal and its transform. Now we'll move to the second part. So this is the second part, which is equal to e raised to minus 3t into u of t. So the Laplace transform can be written as 1 by s plus 3, and the ROC of that particular signal is sigma greater than minus 3. And we can verify that whether there is a common area for this particular signal. And here one signal x is minus 2 and one pole at minus 3. And for the first signal the ROC is sigma greater than minus 2, means towards right. And for the second signal the ROC is sigma greater than minus 3. So for if we combine these two signals, there is a common area. That common area starting from sigma greater than minus 2. So I can mark the common area, which is one is minus 2 and another one is minus 3. And for both signal converge when sigma greater than minus 2. So I can say that the combination of the two signal exists, and the ROC is sigma greater than minus 2. And the combined result we can write, that is x of s can be written as 1 by s plus 2 plus 1 by s plus 3. So I can simplify this, it becomes s plus 3 plus s plus 2 divided by s plus 2 into s plus 3, and the numerator you can write, if we take it becomes 2 into s plus 5 by 2, and denominator will be the same, so s plus 2 into s plus 3. Okay, from this you can say, and the sigma is greater than minus 2, and here you can see there is a 0 also, so if you create the numerator you will get 0, which is at minus 5 by 2. So here we can indicate minus 5 by 2 as a 0. So 1 0 and 2 poles. So this is the final answer. Now we'll move to the next question. Find the Laplace transform of the signal, which is e raised to minus 3t into u of t plus e raised to 2t into u of minus t. So one signal is causal and another signal is anti-causal. So we need the two results. One is e raised to minus 80 into u of t, and another one is an anti-causal signal. Okay, these are the standard result. So here it is u of minus t, and I can write the result. So based on the result, e raised to minus 3t into u of t, the Laplace transform of this particular signal becomes 1 by s plus 3, and the ROC will be sigma greater than minus 3. And coming to the next signal, if you compare with the standard form, it is e raised to 2t into u of minus t. This u of minus t indicate it's an anti-causal signal. If it is an anti-causal signal, in the form minus e raised to minus 80 into u of minus t, you can write 1 by s plus a. Here there is no minus, so definitely there will be a minus in the right side because there is no minus. Okay, and another point, here it is minus a, here it is plus, so the result will be like this: 1 by s minus 2, and the ROC will be sigma less than 2. So we'll get two signals, and we can verify whether there is a common area for this particular signal. And here one signal exists when sigma greater than minus 3, so this is minus 3, and greater than minus 3 means towards right. And another pole, another signal exists 2 and less than 2. Okay, so actually there is a common area between, so actually the first signal, the ROC goes up to infinity, for the second signal it goes up to minus infinity, but the common area is from minus 3 to 2. Okay, so I can combine the result. So I can write x of s is equal to 1 by s plus 3 minus 1 by s minus 2, and after simplification you will get s minus 2 minus s minus 3 divided by s plus 3 into s minus 2, and numerator becomes, so these two s cancel, so remaining is minus 5 by s plus 3 into s minus 2, and the ROC exists from minus 3 to 2, so you can write like this, and the final ROC also you can plot. It's from minus 3 to 2, so this is minus 3 to 2, so between these two areas, so this is the ROC. And one more point, when you do this problem, you always mention that you are applying linearity property. So here you need to write based on linearity property, you can write like this. Okay, So when you do the problems on exam point of view, always write the linearity, based on linearity property you can write like this, and you should also mention the linearity property. Okay, if you know the transform of the two signals, for example x1 and x2, and the combination of the two signals are given, then the Laplace transform will be similarly the combination of the two signals. Okay, so always you need to mention this linearity property when you do problems with property. Now we'll discuss next question. Again, it's a combination of two signal. One signal is causal and another one is anti-causal. Here it is e raised to 2t into u of t, and next one is e raised to minus 3t into u of minus t. Again, we need the standard result here. We can use the standard result. One signal is causal and another one is anti-causal. So based on that you can write, here it is e raised to 2t into u of t, and the Laplace transform of the signal is 1 by s minus 2 and the sigma greater than 2. Okay, here it is, if it is minus a, it becomes plus a, so here it is 2, so definitely it will become minus 2. And similarly you can write the next question, next part, e raised to minus 3t into u of minus t. So based on the anti-causal signal, you can write it becomes 1 by s plus 3 and sigma less than minus 3. So we got two signals. Now we can check whether there is a common area, or we can verify the ROC. So in this case, one signal x is minus 3 and another one at 2, and the first signal, this anti-causal signal when sigma less than minus 3, and another signal exists when sigma greater than 2. So we can see that there is no common ROC. So no common ROC. So Laplace transform does not exist for this combination. So x of s does not exist. Okay, and there is no common area. So you can write x of s does not exist. Individually that signal exists, but the combination does not exist. Now we'll discuss another question. Here you can see that three signals are there. One is del of t and another one is causal, e raised to minus t into u of t. Again in the last portion, again a causal signal. So we need some standard result. We already discussed the Laplace transform of del of t is 1 and ROC is the entire S plane. So now for the causal signal, it will be like this. So I can write the result based on this property. So the Laplace transform of this particular portion becomes 1 by e raised to minus t into u of t becomes 1 by s plus 1. Okay, and ROC will be sigma greater than minus 1. And for the second part, e raised to 2t into u of t, the Laplace transform will be 1 by s minus 2, and again it's a causal signal and sigma greater than 2. Okay, and now here you can see that the ROC can verify. So for del of t signal, ROC is entire S plane. So anywhere you can find the Laplace transform of del of t. And another point, here it's sigma greater than minus 1 and here it is sigma greater than 2. So we need to combine these two results. So finally you can verify here. So one signal minus 1 and it is greater than minus 1, means towards right, and the second signal, the pole is at 2 and again sigma greater than 2. And here you can see that the first signal, the entire S plane. Okay, and for the second signal is only greater than minus 1 and third signal is greater than 2. So the combination of the three signals, if you check, the ROC is sigma greater than minus 2. So I can say that for the resultant signal, ROC will be sigma greater than 2. Okay, that's a common ROC. So we can write the result like this. For x of s, the first signal is del of t. Okay, for del of t, the transform is 1, and second signal is minus 4 by s by applying the linearity property. Okay, we need to mention that as a linearity property. We can write the combination, and the result is 1 by s plus 1, and next term is constant is 1 by 3, so you can directly multiply by 1 by 3, and the answer is 1 by s minus 2. Now we can simplify this, so you need to take the LCM, and after that you will get 3s plus 1 into s minus 2 minus 4 into s minus 2 plus s plus 3, and denominator s plus 1 into s minus 2. Okay, after simplification you will get like this. Denominator there is a 3 also, so 3 is also there, and after simplification you will get s minus 1 the whole square divided by s plus 1 into s minus 2. Okay, and the ROC is sigma greater than 2. And now we can see the different poles. One pole at minus 1 and another pole at 2, and you can see that 0 is also exists at s is equal to 1. So at s is equal to 1 you will get 2 zeros. Okay, so here if you equate this part, you will get s is equal to 1 1 because it's s square, and denominator it becomes s is equal to minus 1 and s is equal to so. So this is about the second signal. Okay, so this is the final result. Now we can discuss the solution of the previous lecture practice question. The first signal is sine omega 0 t into u of t. Okay, you can write this sine omega 0 t in Euler's formula. So e raised to g omega 0 t minus e raised to minus g omega 0 t by 2g, and there is a u of t also. And if you multiply these two, you will get two signals. Okay, one is e raised to g omega 0 t into u of t. Okay, 1 by 2j is there. We'll take only this much part. Okay, e raised to g omega 0 t into u of t. Okay, so this is the first signal, and if you write the Laplace transform of the signal based on the result, it becomes 1 by s minus g omega 0. So in place of a, it is g omega 0, and we'll take only real part. So real part here, it is real part of, so in this case real part is 0, so you can write sigma greater than 0. And second signal, if you take e raised to minus g omega 0, it becomes 1 by s plus g omega 0, again a causal signal, so again sigma greater than. So we can combine these two results, so we'll get x of s like this, 1 by 2j is here, and remaining is 1 by s minus j omega 0 minus 1 by s plus j omega 0. Okay, if you combine this, it becomes omega 0 divided by s square plus omega 0 and sigma greater than 0. So the ROC will be like this, sigma j omega, and this is the s plane, and sigma is equal to 0 is here, and it is greater than 0, means towards right. So this is the ROC. Okay, this is a standard result. You need to by heart the result also, sine, cos, etc. Now we'll discuss another two signal. First signal is u of minus t. Okay, by using the standard result, you can write minus e raised to minus at into u of minus t is 1 by s plus a. It's an anti-causal signal, and if you look at this particular signal, if a is equal to 0, you will get simply minus u of minus t. Okay, so we can write the Laplace transform as 1 by s because a is equal to 0. So is an anti-causal signal, so sigma less than 0 will be the ROC. So this is sigma axis and this is j omega, and sigma less than 0 means towards the left of j omega axis. And if you look at this next signal, again is anti-causal signal, but in the first question there is a minus, there is no minus in the second question. So you can also write like this, u of minus t. Okay, in the result there is a minus. Okay, in the standard form there is a minus, so there is a minus missing, so you can multiply with a minus 1 by s, and is again anti-causal signal, so sigma less than, so ROC will be same. ROC will be left of j omega axis. This is ROC. Now we'll discuss the next question. Again, it's an interesting question. You need to take some care in this particular when you do this problem. And here it's e raised to minus a modulus of t. A similar question we attempt in lecture 4. Now it's a practice question. There's a special case, a is equal to minus 2, but we will discuss both. So here it is e raised to minus a modulus of t. When there is a signal, you need to take two cases. When t is positive, so here t is positive and here t is negative. So t is positive and here t is negative. So you need to take two cases. So here it becomes e raised to minus a, and t you need to consider as positive. So e raised to minus at. Here t is taken as negative. So function will be like this. So here you need to write e raised to at. Now we can see that this particular signal, okay, this signal exists only from 0 to infinity. So it's a causal signal, means you can multiply or you can represent this signal like this, or in other words you need to write e raised to minus at when t greater than 0 and e raised to at when t less than 0. So that is a signal given. Okay, instead of writing this lengthy statement, you can simply write e raised to minus modulus of t. So otherwise we need to write two cases. You can write one more way. This signal exists, the first signal exists only when t greater than 0. So you can multiply it with u of t, because u of t exists only when t greater than 0. Similarly on the left side, this signal exists only when t less than 0, means it is an anti-causal signal. This is the second part, okay, when t is negative. So either you can write in this way, the combination of two signal, or by using the limit you can write t greater than 0 and t less than 0, or in a simple way x of t is e raised to minus a modulus of t. And here the case is different. If a is positive, for example a is 2 or something, you can verify that e raised to a is positive. For example, if a is positive and t is tending to infinity, so if t is tending to infinity, it becomes e raised to minus infinity. E raised to minus infinity means 0. Here t is tending to minus infinity. If you substitute here, it becomes e raised to minus infinity, means 0. When the signal goes to infinity, it becomes 0. So this will be the shape. But here the case is different. Here a is negative, or we can take one example, it's minus 2. So your result becomes a is negative, so already there is minus, and minus 2t. So it becomes e raised to 2t, e raised to 2t into u of t. And the left side, already the signal is e raised to at, and if you substitute a is equal to minus 2, it becomes u of minus t. Okay, so that's difference. And when t is tending to infinity in the positive side, you can see that the result becomes e raised to t into infinity. So you will get e raised to infinity. E raised to infinity is infinity because the signal goes to infinity. And the second side, you can see that t is tending to infinity. Sorry, t is tending to minus infinity. And if you substitute minus infinity here, it becomes e raised to minus 2 into minus infinity. So again it e raised to infinity. So signal again goes to infinity. So that's why the shape is different when a is positive and a is negative. Okay. Now we can check the Laplace transform. So here the signal is e raised to 2t into u of t, and here the signal is e raised to minus 2t into u of minus t. Okay, here it is u of minus t. So this is the shape of the signal. Now we can find the Laplace transform. So here the Laplace transform will be based on this anti-causal signal. It's 1 by s plus 2 and sigma less than minus 2. And here for the causal signal, the result is 1 by s minus 2 and sigma greater than 2. So if we take the s plane, here 2 and here it is minus 2, and one side is greater than 2 and the other side less than minus 2. So there is no common ROC, there is no common ROC, so x of s does not exist. But if A is positive, the case is different. That we if A is positive, we can find the Laplace transform that we discussed in lecture 4. Okay, you can also watch lecture 4 for when A is positive. Okay, thank you.